Let me just say, it's a pleasure to host Karim Adiprasito for our virtual seminar, and he will talk us about the Lefschetz theory beyond positivity.
Yeah.
So please, Karim, go.
So what I will talk about is something that first I will start with something that I will bore Corrado and Martina and Giovanni with, and this is just a rehash of. Sorry. What is this now? No, it doesn't. No.
I see a white page. Is it correct? I see
yes, but it should be writing now. It does something weird at the moment. Now it's okay. Sorry. Now
it's fine.
Okay. Okay. All right. So I want to start with some of the basics of bias pairing theory. What is this? Maybe okay. So I don't know what this is, but maybe. Come on. Okay, so this is something with the hardware, because currently something is not working. Let me see. Sorry, something. No, he's not writing as usual. Okay, so something is not working here with the canvas.
Maybe you can restart the app.
Yeah. Okay. Okay. Let me try to restart this app. Come on. Okay, it's red, but it works. Okay. All right, so I want to first start with the basics of giving a basic introduction to bias pairing theory. And the Lefschetz theorem beyond positivity. And this is something that I presented last summer in Rome, last spring in Rome. And then I want to go a little bit beyond this, and I want to look at something recent, which is spectral gaps. And applications to the Singer conjecture. And that's essentially the premise. And so let me first state the underlying theorem, and maybe let me compare it to the classical situation. So what do we start with in the classical situation? I will immediately do it in a language that is somehow suitable to a generalization or to a comparison. And this is the classical language. We have the Lefschetz theorem for projective complete smooth toric varieties, right? So we have sigma fan simplicial complete Pern in RT, and we assume it's projective, so that we have L, a convex function, on sigma that is a piecewise linear function on sigma whose domains of linearity are exactly the cones of sigma, are the cones of sigma. All right. And then what we have in addition to this is we have a ring P of sigma, and this is the ring of convex polynomial functions. On sigma, and A of sigma, the Artinian reduction, is the quotient of P of sigma by the ideal generated by the global linear functions. All right. And now, after I have introduced all these objects, I have two central theorems, and this is essentially a slightly more general version than the hot Lefschetz theorem and the hot Riemann relations for the associated toric variety, right? So for the algebraic geometers, which I guess many of you, I mean, at least remember this. So we have a toric variety associated to it. L is then the class of an ample function, an ample class, ample class. And A of sigma, this is really just a Chow cohomology ring. All right, and so the statement of the theorems are, all right, that the hard Lefschetz is that this class AK to AD minus K sigma, that this class induces the isomorphism that is given also by the Poincaré duality. So we know that these vector spaces here are isomorphic by Poincaré duality, but we want to realize it by an isomorphism supported in the ring. All right, and this is exactly the isomorphism. So L to the D minus 2K. All right. So reminder, we have a perfect pairing between AK and AD minus K sigma to AD of sigma isomorphic to the reals, where D is the dimension of sigma. All right? And this is, okay, so this is a classical hard Lefschetz theorem. And it comes in tandem with a theorem that is of similar importance. And this is the Riemann relations. And in fact, these two theorems, they always in some form or another come together. So when you prove one, you almost always prove the other as well. I mean, standard conjectures are kind of an exception at the moment, but at least it's conjectured that they still hold. So in some way, they come married with each other. They are in some way, at least conjecturally, always inseparable. And the Hodge-Riemann relations say, okay, so if I have this isomorphism and this pairing, then I can combine this into a bilinear form by saying, okay, I take AK times AK, and I map it to AD of sigma. And I always somehow omit the sigma because, well, it's always sigma here, okay? All right, so now what about this pairing, right? Lefschetz just tells us that this pairing is perfect, right? It's non-degenerate. But the statement is, and this is rather beautiful, that if I take this following subspace, PL-AK, and this is the kernel of AK to AD minus K plus 1, induced by the multiplication with the Lefschetz isomorphism plus 1 copy of L, then PL of AK, then QLK is definite of sine -1 to the K on PL. And this is one important theorem, right? It's behind many of the striking theorems that we have in this area over the past few years. So the Hodge-Riemann relations, they come in when you want to prove, for instance, the log concavity of matroid polynomials. So, I mean, so one important application of these is log concavity of characteristic polynomials. And then there's the work of Elias and Williamson concerning positivity of the Kastanusik polynomials. So positivity. KL. This is Elias Williamson. This is by myself, Johnny Ha, and Eric Katz. And this is kind of the part of the story that is somehow there up till now. So this is a classical Hard-Lefschetz theorem stated in this language of piecewise linear functions. Right? It's a kind of beautiful little way of phrasing it without ever going to a toric variety. And this is okay. So this is a theorem that is classical by now. I mean, there's still the open questions. So whether it's in a certain case or another case, you have this type of a theorem, and under which conditions precisely, right? There's standard conjectures to open. There are people that try to make this work in a tropical world. All these kind of cases, right? So this is a classical case. What I want to talk about today is another theorem, and this is something where you totally forgo positivity or projectivity. So what do I mean by projectivity or positivity? So the crucial thing here is that I assume that there exists L convex supported on sigma. I mean, without this L convex, all these theorems are still true, but they are just empty, right? So I really need this L to be a convex function for both these statements. And otherwise, it's but it's just not true. And it turns out that there are many situations where you can dream up simplicial complexes or cone complexes that are interesting for one reason or another, but you will never know, well, you will never be able to construct a convex function on them. So for instance, I could take a numerical argument. So there's the numerical argument. Arguments is that I could take that is due to Alon. On the other hand, well, Alon gave the constructive part and somehow Milner-Thom. And this is basically most simplicial fans are not projective. Most simplicial fans are not projective, meaning that they don't have a function like that. Or you could even, I mean, this is somehow, okay, so this talks about complete simplicial fans, which a priori, they're already topologically restricted. But because, for instance, they have to immediately be, if you have a complete simplicial fan, you immediately must be a PL sphere. But you could also just abstractly think about some kind of a cone complex over a triangulation of a over a homology sphere, right? So you start with a triangulated sphere. Let me make it in another color, risking that I break it again. All right, so this is some abstract sphere that you could have, and then you could just glue cones together along it, and you still have this ring. All right, it turns out somehow that's not so important, this step of the construction, but okay, so you can still construct this ring, and it turns out that this is a very important question, that somehow whether this in some way Lefschetz still holds, but when you don't have projectivity. And okay, so there is one part, if you want to construct this ring, that is tricky. So P of sigma you can define for any abstract cone complex. So just cone complex for me is just a collection of simplicial cones that share of abstract simplicial cones that share a common point, a common cone point, right? Really just a simplicial complex, and then you take simplicial cone over every single simplex of this cone, simplicial complex. So this you can, P of sigma is still well defined for an abstract thing. But for A of sigma, all right, so what you need for A of sigma is a notion of global functions, right? So P of sigma, more global functions. But you could just take also, okay, it's enough to take an abstract map from this cone complex into Euclidean space of the same dimension in such a way that if you have a d-dimensional cone here, it maps to a d-dimensional cone here, but they can intersect in some weird way. So, for instance, abstractly, this way here, they can overlap in the image. All right, so this is still for me a nice embedding, and then you still have this notion of global functions. So I just defined for you a ring that still has all these nice properties. And for instance, you can show rather easily, and this is an easy exercise in commutative algebra, if sigma is the cone complex over a rational homology sphere, so rational homology sphere of dimension d-1, then the Poincaré duality still holds. So A of sigma in degree k times A of sigma in degree d minus k. This maps to the reals, and this pairing is perfect. All right? And this is just Poincaré duality. Let me write it out. All right. So this is organized and simple enough. But then you can ask yourself, well, does the Lefschetz theorem still hold? So let me answer this question first before I say what the motivation for this is. Okay, so I gave some motivations for the other theorems, for instance, the log concavity of the coefficients of the characteristic polynomial and positivity in the Cauchy-Leuci polynomials. Now let me do the same thing here. Let me do the same job here. All right, so what can I do here? So first of all, I start again with sigma, a triangulated homology sphere. And it's enough if this is a homology sphere with rational coefficients. Okay, so I don't care about any torsion. Of dimension d-1, so that the resulting cone complex is of dimension d. And then what I do is, okay, so then the statement is a little weird, because what it says is that, okay, so I take A of sigma, a generic Artinian reduction. And for the toric geometers, I will give an intuition later. But let's just say on this level, right? I have a lot of choices of maps of sigma for this cone complex into RD, right? As long as I'm in general position, any map works. So I have a whole moduli space, and here I am saying I take an element from an open dense set. Right? There's an open dense set of these Artinian reductions of P sigma that is acceptable to me. And then I take L, a generic element in A1 of sigma. All right? And then the statements, I want to have statements that are in parallel to the Hart-Lefschetz and Hart-Riemann relations, even though they now will not stand at the same height. And indeed, so under this choice, the Hart-Lefschetz theorem is unchanged. Hart-Lefschetz. All right, so we have Hart-Lefschetz that the map from AK to AD minus K sigma induced by the multiplication with d to the minus 2k is an isomorphism. And the second property, let me maybe delete the Poincaré duality here, some space. All right, so on the left side, in the classical situation, I have these Hart-Riemann relations, which are very nice and beautiful. They tell me something about the signature of this Hart-Riemann pairing. So I use something, I basically return to the Hart-Riemann pairing, QLK, and I already know that this is a non-degenerate pairing on AK. All right, this is already a perfect pairing on AK times AK to the reals. All right. And now, what is nice about this pairing? Okay, so what replaces my these Hart-Riemann relations? So the Hart-Riemann relations said that I'm of a specific signature at some subspace. This I can no longer expect, right? L is just some generic linear form. It's an open, chosen from an open dense set. Instead, it takes the following form: that at all ideals I in AK or in A of sigma that are square free monomial. I will explain what this means in a second. The pairing QLK is perfect when restricted to IK. All right. So this is called the Hall-Laman relations, and it's a little unfortunate that the acronym is the same as Hart-Lefschetz, but these are some of the names that somehow the two people that somehow in some way stated something that was a precursor to this kind of statement. Okay, so in some way this is somehow these were the closest precursors, so I had to use their name in some way. So these are the Hall-Lamar relations, and you see that there's a kind of, instead of saying something that on a single subspace, cut out by the Lefschetz isomorphism, I am of a specific sign, I'm now saying something about many subspaces where this quadratic form should not degenerate. Right? And this is somehow not entirely standing on its own if you look at the current literature. So if you look at, for instance, the current work of Karshan and Ziegler, so this is Tammy Ziegler, or you look at the work of Beauregard, then what they look at is what can you tell about the polynomial or about the function if you know that in many slices, in many sections, you have some nice algebraic property. All right? For instance, what can you tell about the polynomial if you know that the restrictions to many subspaces are of a low rank? This kind of things. So, and this here is a kind of is a similar statement in this vein. I will now explain in some way why and how this is related to the Lefschetz property. I will try to give you an idea. Let me first formulate a corollary of this. Okay, so corollary, and this is already interesting. Yeah, let me just consequence. Is that okay? So now let me start as follows. So I still have my sphere sigma as above. Then for generic a sigma, the ideal, if I can look at the Poincaré pairing, AK times AD minus K, sigma to the reals. And I can restrict this to any ideal. All right? I have an ideal, if this is in degree K, and this is in degree D minus K, and I can restrict to this pairing here. And let's say K is less than D half. Then the pairing is non-degenerate in the first factor. And that's already something remarkable. And here I should say again, I is square monomial. And what does square monomial mean in this case? So it just means that I square monomial means that it's of the form A of sigma to A of delta right? It's a kernel of the map where delta is a subcomplex of sigma. Right? So they are cut out by the combinatorics. This is what is meant by a square monomial idea. And this is a rather interesting property. It stands orthogonal on saying that the variety is smooth. So let me draw you, or let me give you a very nice toric variety that satisfies this somehow, that is smooth and projective and anything, but does not satisfy this. So where the genericity really comes in. And this is just P1 cross P1. Right, so the associated polytope, if you draw, I mean, you can draw the primal or the dual is just the cross polytope, or the fan over the cross polytope. And okay, so this is the It's a fan. And now if I say, okay, I want this for k equals 1, all right, this is our dimension 2, so this satisfies my condition. And I take delta subcomplex here. This is delta. This is sigma. And I take I equal to the kernel of A sigma to A delta. And it is this somehow the ideal in degree 1. So this ideal is generated by the prime divisor of this vertex. So it's generated by this ray up there. And you can show that xv times xv is equal to 0. Therefore, this property up there is not satisfied. So consequence not true. Is not true. All right. So the lesson here is that here it's really generic. All right. So I want a generic element of A sigma. So what I think, what I can do is I can change the torus embedding a little. I can perturb any. So one way to state this is I can perturb any simplicial fan into a general position, and the position you can actually specify precisely. This into a general position in such a way that now this deformed fan has the property, satisfies the consequence. And this property here I call the biased pairing property. Because instead of a perfect pairing, what you have is a pairing that is non-degenerate only in one factor. Okay, so let me give you two applications because let me give you two applications of this theorem and why it is important, and then let me sketch to you why this biased pairing property is related to the Lefschetz theorem at all, and then I want to give you somehow an application that goes beyond that. Okay, and application 1. It's the so-called Grünbaum conjecture. And this starts with this observation that if you have a graph that you can embed into the plane, then just the Euler-Descartes formula tells you that the number of edges is at most 3 times the number of vertices. Using the Hall-Laman relations, using the Hall-Laman, you can generalize this to higher dimensions. So what you get is that almost, if delta is a simplicial complex that embeds into R2D, and there's a slight caveat, we need the embedding to be sufficiently nice. So let's say a PL embedding. Then the number of D faces of delta is at most the number of D minus 1 dimensional faces of delta times D plus 2. That's one motivation. The second motivation is the so-called G theorem. And this means that I can, let me state it shortly, saying that the face vectors of triangulated spheres are fully characterized, and you can say it as follows as somehow. Let me just say they are fully characterized. By Okay, let me not go into this too much. By McMullen's conditions, so you can fully characterize what phase numbers a sphere can have, right? So, for instance, a one-dimensional sphere you can see is rather easy because, okay, so you have vertices and edges, and the number of vertices is to equal the number of edges. And in higher dimensions, you can write down all the conditions that are necessary and sufficient for this, for a specific vector of integers or positive integers to be a phase vector of a sphere. And these are two motivations. Let me sketch why this bias pairing property is important. Where does it come from, and how does it imply the Lefschetz theorem at all? So, sketch. So let's say we are in the situation where the fan, where D is of dimension 2k plus 1. All right, so we have an even dimensional sphere. Sigma sphere of even dimension 2k. All right. So what has happened then? Well, okay, so let's look at the most interesting Lefschetz isomorphism. And this is isomorphism between degree k and degree k plus 1. All right. So this is already, so this is kind of, I don't have any powers in this kind of Lefschetz isomorphism, but anyway, so this is kind of the first interesting Lefschetz isomorphism. It turns out this is the most important one because you can reduce all the Lefschetz isomorphism, all Lefschetz problems to this case. So how do you construct a map here? All right. So for this, let me introduce something called the transversality of primes. So the transversal prime property. And what is this? Well, let's say I have a subset W of the vertices, sigma. All right, and then I could look at the generic linear combination. I will denote this by this. So this means if I have this in quotation marks, this means I have a generic linear combination rather than a normal just the sum. Right, so I have some generic coefficients, xv, v, and w. All right, and this, okay, so let's say you look at this map from, right, I always look at this map from ak to ak plus 1, right, this Lefschetz map. So then I want to have that the kernel of this map is as small as possible. So let's say the smallest possible would be that the kernel of a generic combination would be the intersection of the kernels of the individual maps. All right. All right. So now, if this property is true, then, and let's say this property is true for V, for W equal to the vertex set of V. So then we are done, I claim. Done. Lefschetz holds. Does everyone see why this is true? Is everyone still there? Okay, so I hear nothing, but let me just explain it. The reason is that the intersection of over V over all the vertices of sigma of this kernel is equal to 0, and this fact is equivalent to saying that we have a Poincare duality algebra. This is Poincare. All right. So this is all good and nice. So simple property. And now, what I want to do is, okay, so now how do I prove this property? Well, how better to prove something than inductively? All right, so let's say I want to prove this inductively, and here's a simple little lemma. And this is really linear algebra only. So alpha and beta are linear maps from X to Y, real vector spaces. And really, it doesn't really matter that they're real. They only have to be infinite. And then I want to say something. I want to have the kernel of, let me make some room. I want to have the kernel of alpha and beta in a generic combination as small as possible. And what would be as small as possible? Once again, it would be the kernel of alpha intersection kernel of beta. And what guarantees this? Well, the following fact guarantees this. It's a simple little lemma. It's that if I take beta applied to the kernel of alpha, and I intersect this with the image of alpha, then I want this to be 0. All right? And then I have this implication. All right, so let me spend 2 minutes explaining why this is related to bias pairing theory, and then I want to sketch one new application of this whole business. And this is the following, okay, so let's say we want to try to prove this, right? We want to show that the beta, okay, so alpha, we want to show this transversal prime property for all vertices, for W equal to the vertex set of sigma. All right? But why don't we do this by induction, adding vertices one by one? So W is really the first vertex, the second vertex, and so on. All right, and now we add, so let's say we have, so this is, first of all, at some point we have a subset, and now at this point, we want to add a new vertex, xw I plus 1, or we want to add a new map to this, right? So we have the sum over these variables, and this is my alpha, and my beta, that's just the new variable that I want to add, right? The new prime divisor. All right, and I want to generically combine them. All right, X for me is just AK of sigma, and Y is just AK plus 1. All right, so then, okay, so then what I have is X times Wi plus 1, X of Wi plus 1, it's the new vertex, times the kernel of alpha. Okay, so this is really just a pullback to this prime divisor, intersection the image of alpha. All right, so, okay, so I don't know what this, I mean, if they intersect, if these two intersect, all right, this and this, they have to intersect inside the ideal generated by xw I plus 1. All right. So what I can do is I can restrict to xw I plus 1 in the following sense. I can take x alpha and then intersection image of alpha of these two ideals. Sorry. All right, and we want to show that this is true. But now what do we have, right? The kernel and the image, they are naturally orthogonal complements. And they are orthogonal complements in this pullback. And then what you're trying to show is that two orthogonal complements, all right? Trying to show orthogonal complements intersect trivially. All right? And in orthogonal complements intersecting trivially, well, this is just saying that the Poincaré pairing restricted to well, either the pullback, it doesn't matter which of these subspaces I choose. All right, so this is the first subspace, and the image alpha is the second subspace, is perfect. All right, that's just it. All right, so now I told you why this pairing being perfect at subspaces is important to construct a Lefschetz map step by step. All right, so now, because I wanted to talk about something new, so this is all something that is somehow, from my perspective at least, somehow older business, and some of you have heard me talking about this before. So let me talk about something new. And this is the case of the Singer conjecture. And what does the Singer conjecture do? Well, we start with a manifold that is a spherical, M a spherical manifold. Manifold of dimension D. And what do we do? Okay, so this is here, compact, closed, everything. And one of the key things that you want to show about this manifold is, well, one of the key conjectures is that the Euler characteristic changes with the dimension. So the Euler characteristic of, so let's say if D is equal to 2k plus 1, where k, okay, so now it's if it's odd, then you want to show that the Euler characteristic of M is of sign minus 1 to the k. Right, this is the so-called Hopf conjecture. And the Singer conjecture, which implies this by basically a T.S. Singer, says that if I take the universal cover of this manifold, and I take the L2 cohomology of it, so Hi of M tilde, and then let me we follow the notation of Davis and Kuhn and add a little 2 up there. So the L2 cohomology is trivial if I is not equal to, or let me write it like this: 2I is not equal to D. All right, except in everywhere except for the middle, the L2 cohomology should be non-trivial. And the new results, and I kind of run out of time now. New results of myself and a student of mine, Keva Yashve. It's very, very bright and had a small. So, I mean, he will be a very good student. Was an amazing work. And this is true for a special case for M, the Davis Kuhn complex of a right angle Coxeter group. And so let me just describe to you how this is constructed. You start with a graph like this. And then you associate to it a cubical complex. And you do this as follows. You start with defining some edges. All right. So this is by drawing an additional vertex in the middle. So let me draw this additional vertex in the middle, drawing edges to the side vertices. And then for every edge in the graph, you draw a square. All right, like this. And now for every three-dimensional clique, so if you had a triangle like this here, you draw a cube over that clique. All right, so yeah, I don't want to mess it up too much, but somehow like something like this. All right. And then you act, okay, so now you have a cubical complex that's now is all surrounding one vertex. And now you let this group act by reflections. Okay, so this group acts by somehow every vertex here corresponds to a reflection. So you reflect these cubes that you start with. Let me draw it like this. Let me draw the simplest example. So let's say you start with this around the vertex associated to the quadrangle, and then you reflect around this axis and get this. And in this way you get in this way you get the universal cover that you desire. This is M. And then the quotienting by this reflection group gets you the original manifold M. All right. And okay, so that's all nice and good. And the result is somehow that for these complexes, Singer is true. And let me just sketch how this is related to the Lefschetz theorem, because I have like 2 minutes left. And so the idea is that what you need to do is you need to relate these classes, you need to relate the harmonic classes inside the L2, right? Some of the harmonic classes which generate L2 cohomology, so the L2 harmonic classes, you need to relate to Tor cohomology. So there's a machinery to relate these two together. And then what it turns out is to say that if you take a large enough sphere, then on the boundary of this sphere, a large enough disk inside your universal cover M tilde, then the boundary of this disk is a sphere that satisfies the Lefschetz theorem. So our boundary of this disk satisfies Lefschetz. And you do not only need to do that, you need to do this in a uniform way as you take larger and larger disks. So what you do is you take a family of compact disks that exhaust M tilde, and you need to show a uniform Lefschetz for the family of boundary sphere di, which means that there's a uniform spectral gap. Or in the end, another way of saying it is that there's a pullback map from di to di plus 1, and then you have a Lefschetz operator on the Hilbert space, and you want to say that you have a linear operator on the Hilbert space, and you want to say that this is a bounded Lefschetz operator, and that's the thing. Okay, I think I'm over time now, so I can go on, or you can ask questions. I don't know what Francesco suggests, or Filippo.
Oh, well, so maybe you can still continue with 5 minutes, or should you
I mean, I can continue 5 minutes, but I don't know how much more enlightening it gets over 5 minutes. I think somehow.
Nice.
Then maybe we can thank you now.
Yeah.